this next section. So, those of you that haven't, well, you're in for a treat. So, I frequently try to give you sort of life tips, like pro tips, how to lead a better life, to be more fabulous, like this guy. You've already learned about my fashion sense. You've learned about how I manage my iPhone, and how I do that stuff. So now I want to show you about housing. So you may have heard of green screens, and so I've been shooting these videos at my house, but I've been kind of trying to downplay it because it looks like, oh, there's a bookshelf with some board games and like a wall. Yeah, this is all fake. That's all fake. My actual house is way fabulouser. So my actual house is I live on a roof, and the family that I talk about is actually my pigeons. See, I think I've shown you some CGI like puppy dog footage. That's all fake. Okay, my real family is pigeons. So to talk about my pigeons, I have 10 pigeons, and they love me, but sometimes they forget that they love me, and I remind them how much they love me by putting them in reminding holes. So in the top of the roof, where the shingles are nice and worn in, I have these little depressions where I can put the pigeons to remind them that they love me. And I have 3 such holes. And when they all forget how much they love me, then I have to put all of the pigeons in the holes. But I love them, and I would never say put part of one pigeon in one hole and another part of the same pigeon in a different hole. So I'm going to put each pigeon into a single hole, and that means that at least one of the holes will have at least 4 pigeons. Easy, right? Don't believe me? Let's use some of my amazing art skills. And right now you can almost smell the ripe shingles from the roof that I live on. And now you can almost see their feathers fluttering as I draw these pigeons as they are in their reminding holes. Now I've drawn 9 pigeons, but I told you I had 10. So if I have 10 pigeons, no matter which hole I put it in, there's going to be a hole with at least 4 pigeons. Here's the thing though. I already told you that I'd been exaggerating a little bit. I didn't want to blow your mind with how fabulous I live. And now that you're starting to see how fabulous I live, I can be a little bit more honest. I don't want you to get overcome with everything all at once. So, actually, in addition to being a fantastic visual artist, I'm also quite a poet. And if you don't know anything about poetry, the basic thing is if it rhymes, it's poetry, and if it doesn't, it's not. That's actually all anyone ever has to know about poetry. I think that's the end of it. So we can use our poetry skills to learn the truth. And the truth is, I don't just have 10 pigeons. I have what's the only number that rhymes with 10? This is poetry. I have N pigeons. That's right. See, N rhymes with 10. That was the poetic secret. And I don't just have 3 holes. What's the only number that rhymes with 3? Only number that rhymes with 3 is T. That's right. I have T holes. Okay? And see, because I've encoded this in poetry, right? I have N pigeons and T holes, then at least one hole has at least... Okay, what's the only number that rhymes with 4? Think about it. You can hit pause and think about what the only number that rhymes with 4 is. I'll wait. Okay, yeah, that's right. It's ceiling n over t. See how that rhymes, so you can... There we go. Ceiling n over t. And that works when n is 10 and t is 3, because the ceiling of 10 over 3 is 4. Right? The ceiling of 10 over 3 is, the ceiling of 3.3 repeating, which is 4. And so this thing holds true for the first scenario that I gave you, as well as more general settings. This has a name, and the name is the Pigeonhole Principle. And the Pigeonhole Principle is sometimes abbreviated PHP. And there are a number of things called the Pigeonhole Principle. You also might hear it called the Box Principle or Letterbox Principle. So if you're looking up stuff about this, the Box Principle, the Letterbox Principle, or the Pigeonhole Principle oftentimes is stated as if I have n pigeons and n-1 holes, or n holes and n+1 pigeons, then there must be 2 pigeons in a hole. But I'm giving you a slightly more general statement. And I want to convince you that you already know the Pigeonhole Principle. So some ways that you've already seen the Pigeonhole Principle in action is if the class average on an exam is 75%, then at least one person scored at least 75%. All right, so it's kind of a formal statement about averages. So n over t is the average number of pigeons per hole. And what we're saying is there must be a hole with at least the average number of pigeons. The ceiling is taking advantage of the fact that these are discrete objects. So I'm not, like I said before, I'm not putting pieces of pigeons into separate holes. The pigeon is a single atomic entity that I cannot break apart. And those of you that would attempt to break apart my pigeons are weird. That's just weird, man. Okay, so if the average on an exam is 75%, then at least one person scored 75%. If I travel 240 miles in 4 hours, I had to be going at least 60 miles per hour at some point. Okay, and I'm getting a little off base here because you might say, Steve, these are continuous quantities and we're in a discrete setting, and yeah. But the idea is the same. If I travel 240 miles in 4 hours, then my average speed is 60 miles per hour, meaning I couldn't have done that. I physically could not have done that if at some point I wasn't going more than equal to or more than 60 miles per hour. Again, in both of these cases, if everybody scores the same, or if I was going at constant speed the whole time, then every hole has the same number of pigeons, which is the average. That's fine. I'm not going to prove this. I think I do have a proof written out in the notes. It's not a difficult proof, but it's a little bit annoying because you have to deal with the case that t divides n and the case that t does not divide n separately, and they work out to be the same thing, but it's a little annoying. So you can look through the notes for a proof. Let's now use the Pigeonhole Principle to prove some basic things. And we'll be using the Pigeonhole Principle more moving forward. Okay, so example. Prove that in any set of 13 people, at least 2 were born in the same month. Okay, so the basic idea here is we've got 13 people, then it's probably pretty obvious. You probably could have done this without ever hearing about the Pigeonhole Principle or my fabulous lifestyle on a roof, to know that there must be at least 2 people that were born the same month, right? But we can prove this formally by using the pigeonhole principle. So proof, and this is the kind of proof that I would look for. We're going to have people be pigeons, and we'll have months be holes. And then by the pigeonhole principle, at least 1 month has at least ceiling of 13 over 12 equals 2 people. Okay, so I use the pigeonhole principle to say, well, if I have 13 pigeons in each, in exactly one of 12 holes, then there must be a hole with at least ceiling 13 over 12, which is 2 pigeons, and the pigeons are people, so there's at least 1 month with at least 2 people. And that, again, it's not that the pigeonhole principle was something that you needed to have the name for before understanding something like this, but it certainly is a way to formalize this phenomenon that we all know about. So we could ask a bunch of similar questions, but I really want to sort of, let me do one more sort of basic example, and then I'll move on to something a little harder. Okay. So prove that in a set of n points arranged on t parallel lines in the plane, at least one line has greater than or equal to ceiling n over t points. That says points, period. It's written a little bit poorly. So think about that while I fix the word points. And of course, again, this is going to be a really straightforward application of the pigeonhole principle. What do I do? So proof. So the points become pigeons. The lines become holes. Since the lines are parallel, I can't have a point on more than one line. So each point is on exactly one line, since the points are arranged on the lines. And therefore, by the pigeonhole principle, there exists a line with at least ceiling n over t points. Okay, so this is, again, such a straightforward application. It's almost not clear how this is saying anything about the world. So I want you to hold on to this for a minute, and then I want to move on to a more complicated application. So just take a second here, and then I'm going to just use the pigeonhole principle, but put some sauce on it, and I hope you'll appreciate how powerful the pigeonhole principle can be. All right, so I'm going to get rid of this. And I agree that these examples are so simple, it's often difficult to see, like, why is this even a thing? How is this even a section in a book? Let's do one more complicated example, and then I think you'll agree this is worth our time. So example, show that in any party with at least 6 people, there are either 3 mutually acquainted people or 3 mutually unacquainted people, and because this is an inclusive or, I'm just going to emphasize that it's an inclusive or by saying or both. All right. So I'll give you just a second to think about this. So we've got at least 6 people at a party. So to move forward on this, we're just going to pretend that we've got 6 people at a party. And then we're going to somehow need to use the pigeonhole principle. Now, I want to warn you. What a lot of you might be tempted to do is say, 6 people. We need to put them into some holes and get the number 3 out. Okay, I'm looking for 2 holes. Aha! The people are either acquainted or unacquainted. Boom, I'm done. That's it. That is not it, because what does it mean for a person to be acquainted? It doesn't. It's not well defined. A person has to be acquainted with someone or unacquainted with someone. So it's not about the people, it's about their relationships. So in some sense, we're having, instead of people as pigeons, we're having relationships as pigeons. And the 2 holes are either acquainted or unacquainted. So, and we're going to assume that we're not going to worry about, somebody's met somebody and the other person is forgotten or something like. We're going to assume either they have met or they've not met, regardless of whether they remember. So, in order to organize my information, I'm going to fix one person. So, pick one person and call them Alice. Okay, Alice starts with an A, so it's a nice name to start with. So now, there are at least 5 other people, and their names are B, C, D, E, and F. Brandon, Charlie, David, Ethan, and Francine. I don't know. This is where you can be creative and come up with names. That's creativity. Right. So, whatever. There are at least 5 other people. B, C, D, E, and F. Now, here's where we're going to look at these relationships. So, I've got A, then B, C, D, E, and F. Now, either Alice is acquainted to 3 or more, or Alice is unacquainted to 3 or more. Why is that? The pigeons are going to be relationships to Alice that is either acquainted or unacquainted, and the holes, the relationship is either acquainted or unacquainted. That the relationships are, A, Alice has met B or has not met B. This is the relationship. And the holes are either what I'm going to call met or unmet. So this is a relationship, how A relates to B, and then it's either a met or an unmet. So what I'm doing here is I'm drawing a line. If Alice has met these people, I'm not drawing a line if Alice has not met these people. Okay, so or you could think of a solid line as met, a dotted line is unmet. So now, by pigeonhole principle, we get either Alice has met greater than or equal to 3 people, PPL is people, or Alice has not met greater than or equal to 3 people, or both. Okay, or both is possible with more people, but from these 6 people, it's not or both. Doesn't matter. Either one of these holds or the other one holds. Okay, so I'm going to call this case 1. I'm going to call this case 2. And let's move forward with case 1. So suppose Alice has met B, C, and D. All right, so let's suppose that this diagram that I have here is accurate. So let's consider B, C, and D. If one of these 3 has met another of these three, they form a met triple. Met means acquainted with Alice. Okay, so, if C has met D, then A, C, D is a triple of people who are all mutually acquainted. Those are people that have met one another. Okay? So if one pair of these is acquainted, then we're done. But if not, then that means B, C, and D form an unmet triple. In which case we are also done. Okay, you see how easy that was? So in the case that a pair of these people have previously met, then they form a met triple with Alice. In the case that no pair of these three have previously met, well, then that's three people that have not met. That's three mutually unacquainted people. So now it might seem like we're halfway done because we dealt with the case 1. But I claim we're actually more than halfway done because case 2 works just the same way as case 1 except the opposite. What do I mean? Redo 1, but switch met and unmet. And we are done. Was that too easy? Was that too quick? That might have been too quick. So let me explain this. What do I mean by redo 1, but switch met and unmet? Okay, let me re-explain this. Let's just read through 1 again, but now every time we see the word met, we'll interpret it as unmet, and every time we see the word unmet, we'll interpret it as met. So suppose Alice has met B, C, and D. If one of these three has, okay, I've got met, so has not met another of these three, okay. I should back up. Suppose Alice has not met B, C, and D. So we can even use the same diagram, but just assume that a solid line means not met, and that a dotted line means has met. So suppose Alice has not met B, C, and D. If one of these three has not met another of these three, then they form an unmet triple with Alice. Okay? So again, if there was if this solid line now is the opposite, it means unmet, and there was a solid line between one of these pairs, that's an unmet triple. Okay, so the sort of the process that gave us a met triple in the first case gives us an unmet triple in the second case. Okay, now let's continue. So that would be done. That would be an unmet triple. If that's not the case, so if Alice has not met B, C, and D, so we've still got these three bold lines. Alice has not met B, C, and D, but there is no pair of these that are also unmet. That means the three of them form a met triple, because here in the previous thing we had unmet, which means now we're in the opposite. That means three of them form a met triple. So where was the pigeonhole principle in all of this? It seems like we've done a whole lot of talking, but the pigeonhole principle was just up here. Well, the truth is, a lot of this was sort of based on reasoning after the pigeonhole principle part. But the point is, the pigeonhole principle was the key step to get us to a place where we could go through a small number of logical steps. Moreover, not only was there a small number of them, but they were sort of the same. They were like mirror images. So we really just did one of these cases, and it turns out that provided the structure or the type of the argument that would give us the other case as well. So just to run through this again really quickly, show that in a party with at least 6 people, there are either 3 mutually acquainted people or 3 mutually unacquainted people, or both. So if I've shown these, I'm not worried about the both case. That would be, with the more than 6. Actually, you could have this. Because you could have Alice has met these 3 people, and they've all met one another, but Alice has not met E has not met F, and Alice has not met F. Then we've got both a met triple and an unmet triple. It's possible, but whatever. Okay, pick one person, call them Alice. There are at least 5 other people, B, C, D, E, and F. If pigeons are relationships to Alice and holes are, they either categorize the relationship is either it's met or unmet, then by pigeonhole principle, either Alice has met at least 3 people or Alice has not met at least 3 people. Okay? Now suppose Alice has met B, C, and D. If one of those 3 has met another of those 3, then the 3 of them form a met triple. Because if Alice has met B and Alice has met D, and just so happens B and D have met before, then A, B, and D are a met triple. If not, that means no pair of these 3 have met, which means we've got an unmet triple. Okay, that was case 1, when Alice has met at least 3 people. Now let's back up and suppose we're in case 2 if Alice has not met any of these 3 people. Well, we're going to redo that same reasoning, just backwards. So if Alice has not met 3 people, let's suppose B, C, and D are 3 people that she's not met. Maybe she's not met others, but at least she's not met B, C, and D. If any pair of these 3 have not met, Alice with that pair form an unmet triple. If no pair of these 3 are unacquainted, that means that all 3 of them are mutually acquainted. That means we've got a met triple. So in case 2, we're done by basically the same reasoning.